the organisers for asking me to come and address this meeting. As I just said, this is all joint work with Nekovar, and we have which is work in progress, although there are some accounts of this which can be found in our paper, which is called Introduction to Plectic Homology, and there are also some slides of various lectures we've given, which you can find on our respective websites. So the theme of this talk is the interplay between three things. So one is regulators, one is motives, and the third is L-functions. So this encompasses at least some of the themes of this program. Here we have Algebraic geometry, here we have number theory, and here we have periods. No physics for the moment. So in particular, what we are interested in is the explicit construction of, well, not so much motives, but motivic elements, which whose regulators give special values of L-functions. And this is a long story with a distinguished history, and in the context of motivic homology, this goes back to conjectures of Bloch and Abelian and many examples that they constructed. So let me start by saying what the picture is, or some of the picture. So the things that are known over Q, so there are lots of known results. Known results. So I mentioned particular Abelian, although historically these also go back quite a long way. So one has information about special values of L-functions for, say, elliptic curves over Q, more generally for modular forms, or rather the motives attached to them. Going back more than 100 years, one has results for the regulators attached to units in Abelian extensions of the rationals, or in Abelian extensions of some imaginary quadratic field, cyclotomic and elliptic units, and more generally for elliptic curves with complex multiplication or Hecke characters of Q minus D. So the original case that Bloch studied was elliptic curves with complex multiplication. It's a very special sort of Hecke character, and these were generalized considerably in work of Denninger. Okay, so these are things that are known, and in these situations, what one has is one has some special element of some motivic homology group, okay, which in this case is just the units, and these cases are some K2 or some more general motivic homology group, and then one applies the regulator map to that, and you get the value of an L function, or let's say the derivative of an L function with some motive, in all of these cases of a negative integer, a non-positive integer. Some. Okay, am I writing large enough for the people at the back? Yep.
How are you normalizing your L functions?
Sorry?
I mean, usually, like for modular forms, L is positive. How are you normalizing your L function? You say your L is it's always negative, but usually it's positive for modular forms between 0 and the weight.
No, these are not pure. I mean, these are non-critical values.
Oh, I see.
These are non-critical values.
Well, you're only talking about the case when it's actually regulated. You wrote periods. So you're not talking about...
Regulators are periods.
So you're excluding the original case of Abelian.
Sorry, I'm excluding the least injection.
The least.
Yes. All right, so for units, one's just looking at the derivative of some characters at s equals 0.
It's the L function of the modular form.
It's the L function of the modular form with the usual Hecker normalization. And the case, for example, for K2 in an elliptic curve is the value of the L function at s equals 0, which is the first place where there's a 0 forced by the functional equation in every case. Okay, so this is sort of taking this as known. Now, what we're interested in is in some generalization of this. So I just want to say that all these constructions of special elements are in some sense automorphic. I mean, they come from the geometry of modular curves or some modular varieties. And so we want to consider some case in which one has some similar geometry, and so for that reason we're going to work over F, which is some totally real field, number field. Whose degree will always be denoted R. So one can ask the same questions about analogous objects. So the analogous objects are well, the elliptic curves over F, or Hilbert modular forms associated to F. The analogous objects here would be units in the Abelian extensions of F, or Abelian extensions of some field K, which is a CM field. Sorry, this way is F adjoin the square root of minus delta. Delta is some totally positive element of F. So the units in some Abelian extension of some CM field. Sorry, that's not very legible, that's an AB, maximum Abelian extension. Or more generally, one could ask about algebraic characters of such a field K. Now, when you look at the analogous problems, in this setting, what you see is that the L function have zeros of order R. So the L function of elliptic curve over F at s equals 0 has a 0 order R in the functional equation. And so what one expects, therefore, is to have to write down sort of R special elements such that we get an R by R determinant which will compute the rth derivative at our non-positive integer of the motive. So a slightly more canonical way of saying that is we like an element of the rth exterior power of this motivic homology group, which gives rise to R.
So maybe you're restricting the characters of F, for example, which are the same signature.
Yeah, I'm not going to be...
Otherwise, you could have order 1 sometimes.
Oh, yeah, sometimes, yes, okay. Yeah, there is certain, I'm not going to say what the exact parameters are, but there are certain restrictions on the infinity of these heavy characters, for example. Now, if you take the trivial character of q, of course, you don't get 0 x equals 0, but it means 8.
Yeah.
Okay, so we have to exclude some cases.
And Hilbert modular forms over the field F, which is the same as the field of definition of elliptic curves, or it could be any other.
No, we'll say over F. So that's the sort of strict analogy of this. Okay, so I would
Parallel
like.
weight 2 as well.
I'm sorry?
Parallel weight 2.
Not necessarily, maybe. I mean, yeah, one. This is we. Okay, this is just a setting. Okay, so all these constructions are modular. So in order to see what one might expect here, one has to look at what it means, what sort of modular. Well, for example, what it means to say that an elliptic curve, which at the moment I will call A, is modular over this field Q or over the field F. So we've got an elliptic curve over Q. Then there are two notions of modularity, which are both known to be true. One has the idea of arithmetic modularity. So that's quite most simply expressed by saying that the L function of the elliptic curve is the L function over 1 over 4. Okay, which of course is known by Wiles, etc. One also has the notion of geometric modularity. So this is the motivic way of looking at it, which is if we look at the motive of our elliptic curve, or the interesting part of the motive, that is a direct factor of the motive of a modular curve. So this is here a compact modular curve. X naught n, in fact. Over Q. And the relation between them is, of course, the fact that one has the one form associated to F. So that's 2 pi I F tour d tour, where tour is the, as all, in all throughout this talk, is just going to be the coordinate on the upper half plane. So that belongs to the F1 under this correspondence of the H1 derived of X over Q. So that's the link between these two things. Okay, so this is known thanks to Wiles, and geometric modularity, the equivalence of these comes from Eichel's-Shimura theory, saying that you can construct even subvarieties of Jacobians of modular curves from modular forms, and Falting's isomorphism. So the equivalent identity of L functions, which means equivalence of L limitations, implies that you actually have something geometric. Okay, now, so this is completely known. So let's call this, I don't know, A and G. And modularity. So over F one has exactly the same notion of arithmetic modularity. I'm going to just say something else. Of course, we know, as even moreover, it's appropriate I should put it at the bottom of the board so nobody can see it for now. But the whole of H1 of X is described by just a bit more than this. We take the H1 of some abelian varieties attached to F. And here we have to extend scalars to say, well, coefficients to keep on mean. And where this is some abelian variety of the cube with real multiplication. Okay, so for elliptic curves over F, arithmetic modularity is just the same. It says that this is the L function here, where this is now a Hilbert modular form. So I've written the same thing there. But this is a Hilbert modular form of weight.
Can you raise the real blank by about 1 foot?
Sorry?
Can you raise the real blank by about 1 foot or so?
Well, if I do what I've just written, it will disappear.
Oh.
No.
I'm going to the rear backward. That's the one I'm writing.
If you're watching the audience a bit more, you see all kinds of people standing up to try and see what they break.
The people in the front should crouch down.
It will come up in a few seconds.
I'm going to move it up in a few seconds.
You have a few pages.
Okay, so, but I will say everything that's written on the board. So tell me if I'm not speaking loudly enough. Okay, so the arithmetic modularity, I will move this up a foot, is given by the equality of L functions where now F is a Hilbert modular form, cos form, parallel weight 2, with other conditions. So the geometric modularity is much more interesting. Okay, this is known in lots of cases. Known for, let's say, many fields. F by the work of many people, which I will not attempt to write down using sort of Taylor-Wiles methods. And geometric modularity is more complicated because on the one hand we have our Abelian variety, which is defined over F, which is a dimension 1, so it has only interest in cohomology in dimension 1. On the other hand, the natural geometric object, so this is a Hilbert modular variety, and that is definitely not, the field of natural field definition for that is Q, not F. So this is, let's say, some compactified. I'll use X for the compact guy, or one of the compact guys. Now, if we take our F here,
That's of dimension R.
yes, it's a dimension R. And it, so now if we take our F here, up there, then that gives rise to an R form. It's 2 pi I to the R. So a Hilbert modular form is a function of R variables in the upper half plane. And this belongs to the FR of the HR duram of X over Q with suitable normalizations. Okay, so what one then expects is that the geometric modularity is given by an inclusion of motives So here, the thing to do is to take all the real places of F, or equivalently all the beddings in Q bar. So basically we take the motive of A and we take all its conjugates and we multiply them together, and this gives us a motive which is now weight R, which is actually a motive over Q.
Is that the same as just multiplying the conjugates of A to get an abelian variety over Q?
Sorry?
Is that the same as the abelian variety over Q, just multiplying the conjugates of A?
I'll just say, wait a moment. Okay, so let's pull this in one. So, I mean, a more precise way of saying that is that we take the motive of A, which is the motive over F, and now we take the tense reduction from F to Q. So this will be induced by correspondence. Okay, what does it mean to say that you've got a, this is a submotive of this? It's going to be induced by a certain appropriate correspondence between X and between, indeed, exactly what Don said, the various restriction scalars, just the product of the conjugates, of A from F to Q. And this correspondence will therefore, of course, induce a map from, well, let's write it this way, from the tensor product of the F1s of the H1 arms of these various sigma rays. Okay, this is moment of truth. I'm not sure if this is the right way to do this. Let's see and see.
Horizontal is better.
Again?
Keep going.
Keep going.
No turn.
No good.
It's a Hilbert modular blackboard, you gotta go back and forth all the time.
So in contrast to the case of arithmetic modularity, its geometric modularity is, I believe, completely unknown. So, in particular, the Hodge-Durham version of this statement 1 would say it's the same as saying, well, it's Oda's conjecture, which says that period matrices of Hilbert modular forms are tensor products. Of 2 by 2 matrices. The situation is better in the L-adic sort of realization. So if we look at the L-adic version of 2, of 1, I'm sorry, of 1, in other words, do we have an inclusion of L-adic realization? Now that's true if A is arithmetically modular, and that's a result of the work of Berlinski-Lebesgue, which tells us what the semi-simplification of the L-adic representations attached to in the cohomology of these modular varieties are, and also Nekovar's semi-simplicity theorem, which says that they're actually semi-simple. So what we can sort of view this as, so it's rather more subtle geometric modularity as, well, what you expect, okay, so let's say we expect in fact that you take the whole motive HR of X. Now, okay, I'm being a bit vague here. What I really mean is the intersection cohomology motive of the minimal compactification. So what we expect this to be, in fact, to be the direct sum, in fact, it's not just for R, it's the image really. It would be the direct sum of some, again, some tensor powers of sigma of something. Okay, so here we have, obviously there are going to be some other Abelian varieties which occur, and there are also some other stuff which I'm not going to make specific here, but one could do. Again, which also holds in the L-adic setting. So we expect that, and this is something like a Kunev formula, except that X is not a product. So we think of this as being a sort of weak Kunev formula. And it comes from the fact that if we take our open Hilbert modular variety, so this is the open Hilbert modular variety, it can be. Its complex points are uniformized by R copies of the upper half plane. This is the upper half plane. And this, of course, is the product. So this is the universal cover. And this is the product. But no finite cover of this is a product. The universal cover is a product, and somehow that should have some algebraic geometric meaning. So this is sort of like, okay, so these things which you can't see, they're arithmetic quarks. So we have physics algebra.
Only if R is 3.
Sorry?
Only if R is 3.
Only if what is what?
Only if R is 3. But they chords.
Oh, okay, yeah. I mean, physicists don't really worry about the number of dimensions of the universe we live in, do they? Okay. Okay, so we can't really see these quarks, but we see some shadows of them. So they're visible consequences. So there are three kinds, two kinds, let's say. The ones two of the kinds we can actually prove. So one, the Hodge theoretic, is that if we look at this complex cohomology of this open variety, well, because it carries a mixed Hodge structure, it actually has something in it which we call a Plectic mixed Hodge structure, which means that if you look at the graded pieces for the wave filtration, instead of just being sums of sort of H PQs, and sums of H underlying PQs, where these now are multi-indices. So this comes from the fact that you've got DZJs and you've got DZJ bars, and this tells you how many of each you've got. Sorry, I call them Z, they should really be called.
What's that?
Sorry?
I don't know what that. What does it mean? You have multi-indices?
Z to the R rather than
I
Z.
know what Z to the R is.
So that
I don't know what
is-
the HPQ.
Sorry?
I don't know what you mean by HP underline Q
Yeah,
underline.
the ones given by the different.
Yeah, P is the one for which-
Details and detail bars.
Yeah, we've got PJ detail J's and QJ detail J.
Oh, I see. All right.
P is P1 up to P.
Those are coming from the different factors.
Yeah. Okay, then analytically,
Is Plectic an existing word? Or does it
ask me again in action. So analytically, one has the same sort of thing if we look at the cohomology. Well, just to be careful, I write with QL definitions. So this, of course, naturally has an action of, call it gamma Q, the gamma group. But there's actually a bigger group, which we'll call gamma FPL, which has got an F in it. So, and this is, well, this is the automorphism for Q bar over Q as a Q algebra, and this is the automorphisms of Q bar tensor F as an F algebra. And this group is isomorphic to, after you make some choices, the gamma of F are copies, semi-direct product with the symmetric group C of R.
Can I ask a small question?
Yes.
I'm sorry, I lost track. So X was, so to speak, a summand of very restriction, but then the Y, I didn't understand much of.
Oh, you know, X is a Hilbert modular variety,
Yes.
compactified, and Y is just the is the uncompactified one. Yeah, just the uncompactified Hilbert modular variety. And so I didn't write.
Compatibilization is a minimal compatibilization.
Well, okay, I mean, let's not worry about that. Okay, I need to make two remarks about this.
So this acts on the cohomology.
Sorry?
So this acts.
Yeah, so this thing acts, yes. So this also acting, so we have the larger group. Acting. And so where does this group come from? If you start with a representation let's call it V of this Galois group, absolute Galois group of F, then if you take well, either the tensor product or the direct sum, well, this is the underlying space of the induction, this is the underlying space of the tensor induction. This is actually a representation of this Plectic group, whose restriction to gamma Q is, well, tensor induction or just the unit induction. And if you look at the Galois homology of this Plectic group into degree R of this tensor induction, what you get is by applying the Coulomb formula, let's say this is an L-adic representation, what you the wedge R of the H1 of the normal gamma group, gamma F of V. So inside this cohomology theory, one gets these exterior powers, and so if one has this in some geometric setting, then one would expect to get some elements of the exterior power have gone, if anyway, but as I mentioned at the beginning of the lecture, exterior power of some cohomology groups associated with varieties, which might be motivic. And since I seem to be going much slower than I intended, let's just say that what we expect, of course, is that there's a motivic analog, motivic version. So in other words, there's a category of, a sort of category of refined sort of Plectic motives. For which this is the representation of this group is the L-adic realization, and these Plectic Hodge structures are the Hodge theoretic realization. Unfortunately, at the moment, we don't have a good candidate for what this category should be.
Is this just sort of a statement about the étal sheaves over schemes over F compared to schemes over Q? Étal sheaves?
Well, somehow, okay, so
It's sort of a general statement about the Galois.
Yes, induced representations are automatically Plectic, but this is not the interesting example.
and this category of motive, Plectic motive, would be something like a category of motives over the R-fold product of, or R-fold symmetric product of spec F with itself over the absolute point. I am not going to write that. This thing doesn't actually exist, but
I didn't hear the last word, over the absolute.
absolute point.
Oh.
You know, it's what people call spec of F1. It's like okay, so we don't have this motivic picture, but we can see, at least rehearse, what its consequences would be for the construction of special elements of motivic cohomology. Okay, so in order to do this rehearse now, we first have to remind ourselves what happens over Q. So let me stick the absolute basic example. So we take this is our modular curve over Q, and then we have a universal, assuming the level is sufficiently small, a universal family of elliptic curves. So over Q, and then we'll take some section here, S, which is of order, a torsion section of order n, greater than 1. And now, usually in this game we have to choose some auxiliary integer, which is prime to 6 to make this work in the best possible way. And then, in the setting, there exists a canonical, okay, let me say this in a classical way. There exists an absolutely canonical function theta, which depends on this auxiliary parameter, of course, which is a function invertible function on the complement of the d torsion, which of course is H1 Motivic 1, with divisor equal to D, which is just the divisor d torsion minus d squared plus, so it's really minus, d squared times 0. That's the basic fact. You can construct this function either by bare hands using classical complex variable theory, or you can have some characterization in terms of its invariance under norm maps for multiplication by n. Anyway, so there is a function with this divisor. This divisor is actually principal, subject to this condition anyway, and there is actually a way of picking out a unique function with that divisor. Now when we evaluate this function, that's this zero section, sorry, this section of fine order,
D is random here?
sorry, D,
What was the
D is some auxiliary number which you don't have to worry about.
Randomly
Could be 5,
chosen.
for example.
Randomly chosen.
5 is good. Okay.
Is it related to M?
Sorry?
Is it related to torsion M?
Yeah. N has to be prime to D. But N you should think of as being some variable large number, and D is just there because equals 1 wouldn't work. Because the actual theta function is not a function, it's invariant. Okay, so this now, we call US. Okay. It's therefore a unit on a modular curve. So that's again D equals H1. So these things are classically called Siegel modular units. If you evaluate them at Cn points, so you can pick some Tor, so that's imaginary quadratic, so C is Q of Tor, K, if it's imaginary quadratic, then we get things called elliptic units. And you have to take some combination, choose D appropriately, and do some messing around. Basically, you can construct units in Abelian extensions of K by taking these guys. And then you can also take cut products and we go on to get the Bayes and Carter elements of A2 of modular curve. Now, this construction, if you do it the right way, works not just for Motivic homology. You can replace HM by any, well, I will define this precisely, any arithmetic homology theory. So meaning Abelian homology, or absolute L-adic homology, so that means L-adic homology. So we take H star of, let's say, of E minus ED with coefficients in some QL with some twist here, and we don't extend scalars to Q bar. So in other words, we've got Galois homology built in. So this. So I mean, these are the cohomology theories which are the targets of regulator maps. And in Deligne homology, so now we look at this thing in H1 Deligne homology of this E minus ED, so with R1 coefficients. Our element is represented by the log mod of this, which is the Green's function for D. So in other words, if we take curly D bar D of G, or G, this is 2 pi I times, so this is the derivative on E, this is on E. So this is taking derivative in the sense of currents, we get 2 pi I times the delta current associated with this divisor D. So some current supported on the D torsion. And if we evaluate this, now S star of this G is a real analytic Eisenstein series. Okay, so this is just one of the many modular constructions of interesting elements. And in some sense, it's the basic one because the other constructions are some not necessarily trivial generalizations of this by taking coefficients and things like that. So now next, we want to look at what might happen over the field F. Now the problem is that we don't have motivic cohomology in this plectic world yet. We do have cohomology of this plectic Galois group, but at the moment, one thing I didn't have time to say was that the action of this plectic Galois group on the cohomology of the Hill modular variety is not very canonical. We don't have a canonical construction of that. We just know it exists. That means one can't really write down this plectic analogue of absolute dialectic cohomology, but we can write down an analogue of Deligne cohomology using this plectic structure. So what I'm going to say now is initially speculative, but in the Hodge theoretic world it will turn out to be explicit and will give rise to L values. So now over F, we'll assume that H is some sort of plectic arithmetic cohomology. So the sort of idea that I have in mind is we might have, let's take this gamma, this plectic Galois group, and R gamma, whatever, with some QL, I know, coefficients, and then there'll be some twist, maybe. Okay, so if we had a variety here for which this R gamma, so this will be something intensive with QR, where this had a sufficiently canonical action of this Galois group, then we could just take this cohomology and that would be our candidate. It's the analogue of the analytic thing, or plectic Deligne cohomology, which I certainly don't have time to even write down an explicit definition of. But one could imagine that such a thing would exist, and indeed it does.
With real coefficients.
With real coefficients. Yeah. With real complex coefficients. Okay, so now the first issue, which turns out to be very important for more than one reason. If we try and take this picture here, is that the universal Hilbert modular, the Hilbert object, Hilbert AV, is not a scheme, it's a stack, because of the presence of units. Well, Q has units, but you've always killed these off by adding some level structure. But you can't kill off the level structure by kill off the action of units just by taking a mod n level structure. So the picture here now is you'll have A down to script y. So this will be some stack of parameterizing Abelian varieties with real multiplication. And so explicitly what this is, so this is, well, the quotient, except the quotient doesn't exist because the action is not very nice, of this, where we have, I'm going to put something else there, so A will be over Y, will be an Abelian scheme with endomorphisms coming from the unit, sorry, OF, the ring of integers of F, and delta here is a finite index subgroup of the totally positive units of F. Okay, so this is a quotient of this. Now, of course, you could say, well, if we put polarizations on, then we wouldn't have this problem, but that's not a good thing to do for reasons that may become apparent. So this is just a sort of classifying space of this group delta. So delta is acting trivially on here, but that's non-trivially on the fibers. Okay, so this guy is a stack. You can't really avoid that. And let's suppose we have some section here, so explicitly S is just a section of this Abelian scheme, which is invariant under delta, and we'll assume that MS is 0, and we'll have our D as before. Now, formally, if we had this cohomology, you could then construct a sort of Plectic element of now this Plectic cohomology. So I'll put P out here. Just this. That. That's 2r minus 1. With the R twist here, with so there's a residue map along here, which is to H0, just AD, and 0 twist. So with a prescribed residue here, with residue of this theta is equal to, let's call it Z, so that's just the analog, it's just the D torsion minus D to the 2 times 0. So instead of having a function with a given divisor, we have this class and this cohomology group with a given residue. So there exists some canonical thing. Now we restrict to our... Okay, I have to say something about the cohomology of these stacks, which I will in just a moment. So we restrict that to Y. So we get this Y, and remember this Y is just a scheme Y product with this I'll call it B delta, this classifying space. You can think of this in many different ways, but some conditional object.
I'm a little worried about that. I mean, shouldn't it be the finite cover of Y modulo crossed with the contractible space on which delta acts modulo the diagonal?
Yeah, I'm going to say that in just a moment.
Sorry?
Yes.
Yeah, but it want to be a product.
Sorry?
It's not a product.
No,
It's not-
delta acts trivially on Y. Delta acts trivially on Y, on this Y, but non-trivially on A. Because we want OF inside the endomorphisms of A over Y, so that means that the units are inside the endomorphism, the automorphisms of A over Y. So this delta is acting on the fibre, each fibre, but it acts trivially on the base. So on the base we just get this classifying space, but here we get this really horrible product. Because, for example, 0 is, or any torsion point has infinite stabilizer, so it's kind of really a bit nasty. So now what you can do is, this is equivariant homology of rho and y for delta, but I mean that doesn't mean very much because delta is acting trivially. So now what we can do is we can take the cat product with the top, with the generator, let's call it eta sub delta, of the highest degree homology of delta, which is just isomorphic to Z. The delta is just a free abelian group of rank R minus 1. So we take the cat product, and we have an HR plectic of Y with this R twist. So this will be here, some element here. I'm going to call it US plectic inside there. So we should think of these as sort of being plectic Eisenstein series. Seem to have run out of time, or will be about to run out of time. So let me just write down a couple of formulae, analogous to these ones. So if I come back to the case of elliptic curve, then one has explicit formulae. Let's go back to Hanukkah and Eisenstein for these S star of G.
While you're racing, can I ask a question?
Yes, please.
If you just took some other non-plectic homology theory, it looks like you could do this construction.
You could, but the result would not be interesting.
Oh.
Well, for example, the problem is you get, if we did the K theory, you get the Arth-Millman K theory of Y.
Yeah.
That is, by Abelian's conjecture, predicted to be zero.
Yeah.
So that's the not clever thing. And by Varson, I mean you. Okay, so I have to write some formulae. So here, let me just write some formulae for this G. So here, G is something like the sum where we think now some gamma is n to all plus n, not equal to 0, of, okay, so gamma, this is the period lattice of your elliptic curve, and now you can write out G as a Fourier series because the elliptic curve is a relative torus. So there are some characters, and then the Fourier coefficient is just essentially modulo gamma squared, except there's something plus times a periodic in. Because of this d, there's a periodic function of m and n which you have to plug. But basically, the Fourier coefficient, gamma Fourier coefficient, is something like 1 over mod gamma squared. And it's pretty easy to check this differential equation. In this case, okay, so in the case of F, and where we take this Plectic Abelian cohomology, then these things are represented by differential forms, so we get something which we'll call a Plectic green current. G, which will have now satisfy some differential equation, which I think I'll write. We'll take the product of R, these holomorphic different derivatives. So these are the partial derivatives in the Zj toward J direction. So we take G, that, and now we apply, well, let's call it D. Now, it's I'm not going to be precise because there's also a sort of derivative in the equivariant direction, which I'm not going to make explicit. Anyway, so this is essentially now 2 pi I to the R times the delta current supported at Z. So Z, we've already seen, but I haven't told you, yes, the residue of, this is the residue of, this is the residue of this theta. So it's just this sum of zero cycle, relative zero cycle, sum of detorsion sections. And now we have a formula for this G. So maybe this is where I'm going to almost finish. So, very roughly, okay, you can write it as a sum of, as a Fourier series. And now gamma is n plus tau plus n, where m and n are now in OF, and non-zero. And again, we get something about, depending on gamma modulo, mod d, in fact. You know? So we get some extra things which we don't worry about. And then you get the norm. So this is the so gamma is in either in like an F tensor with C or even F. Yeah. Well, I'm going to take a projection. So I'm going to take them even as inside. No, in essence, C, and this is Minkowski norm. So we get that. Now, I said this was a form, and if you sort of count your derivatives appropriately, it has to be an R minus 1 form. And so this is multiplied by the R minus 1 invariant form. Now you're going to understand what U is on delta tensor R. Okay, so here I just have to say what this equivariant cohomology is. Yeah? Yeah, I'm going to stop. Okay, so the equivariant cohomology is the cohomology of Y, or whatever it is, tensored with B delta, and here's you have an explicit realization of this. We just take the torus delta tensor R mod Z. So rather than do something simplicial, we take a geometric realization of this classifying space, and okay, then we get that, plus other stuff. The other stuff has the property that now when we take this cat product with e to delta, that's the same as integrating over this torus. And that leads then to some non-homomorphic Eisenstein series. Which is actually a function now, and this gives rise to L values if you specialize to Cn points. Okay, well, the last part I'm afraid was rather rushed, but that's all I have time to say.
All right, any questions or comments? Yes, please.
Is Plectic an existing word?
No. It's a manufactured word.
Manufactured word, and to what properties does it refer to?
Okay, so this Galois group is a Reed product. A Reed product.
Yeah.
And so Plectic, it means woven,
Yeah.
plectos. So that's why it's Plectic. It's not a back formation from symplectic or anything like that, or metaphysitic. It's a freestanding word.
Okay.
So I have a quick question. So you take the Galois group gamma f and you extend it to a bigger group. So there are lots of interesting extensions of the Galois group, like the Taniyama group or Langland's group and so on. Do these things extend the Plectic situation?
Yeah, there's a Plectic Taniyama group. Jan has this paper on complex multiplication. Symmetry.
My attempt at constructing this Plectic Taniyama group was not the right one, but Tony had a student who did something which is a closer approximation of a Plectic Taniyama group.
So there's a reciprocity law generalizing classical one.
There must be, but no one has bothered to work it. Okay, so I proved that this big gamma group acts on the CN points on the divergence in some kind of way which extends the take coordinate.
Oh. Okay.
Next, H2R minus 1 of y cross b delta. Is there something Plectic with b delta, or b delta is just...
Well, I mean, somehow, when you have in this Plectic situation, somehow delta comes free. But the b delta is just b delta. Yeah, there's no, I mean, this is just when we took the cohomology of this. We just take this torus and we take its usual cohomology, by C infinity forms, or by invariant forms if you like. So the plecticity only occurs in the complex structure. So in other words, on the y side.
But this is after taking this pull-by bisection. In
Yeah.
fact, the original thing is not on this product, it's on this usual equivariant gadget you use.
Yeah, so we have to take, yeah, clearly, we have to take A and cross E delta, so this is the modular of delta, where E delta is just delta times R. It's just this contractible space in which delta acts freely. So it's the cohomology of this quotient. So in very concrete terms, we're looking at differential forms on, so this is a capital A, differential forms on A cross E delta, A cross this Euclidean space, which are invariant by capital delta. Okay, and this is an example of such a thing. Yes?
I think the proof of rationality of the L values of F, an Aristotelian real field, and some L values are just powers of R. The proof goes through this kind of series. Yeah.
We are interested in these non-critical.
These are non-critical values. We're outside the critical scope, so it's not just periods. I mean, it's not just classical periods. We have regulators. These are regulators.
If it is H2R minus 1 Plectic A, if you replace if you erase this PL, then usual residue map goes to H2R minus 1 A minus coordination R things and twisted by R,
Yes,
goes to HR minus 1 twisted by 0.
No, it goes from H2R minus 1, we get H2R with supports. By purity, that's H0 with a twist by 0. So the numerology does work with it. I mean, that's the numerology you have to have.
All right, there are no further questions. Let's thank the speaker again.